So welcome. This is the proposal workshop for OSI 4.0. This is the first proposal workshop where we focus on the topics of flat buffers and performance. And there will be a bigger, more general proposal workshop later this year. The purpose of today's meeting is that we want to kickstart a phase where we look at the performance of OSI, and we want to evaluate a possible switch to Google flat buffers for Roadmodel, and we do need some feedback. We do need some feedback from you from real applications of OSI. And other than that, there will be also a general overview of the current developments in the project and a first teaser of what else is planned in OSI 4.0. But like I said, there will be a bigger proposal workshop, a more general one, where we discuss the full content and scope of OSI 4.0 later this year. For the agenda, I will give a short welcome, and then I'm going to talk a bit about ASAM and the other OpenX standards. Kmeid Saad will then talk about the current the developments in the project, and then talk about the path to 4.0. So what is planned, what's already in the pipeline, and he will be supported by Pierre. And in the end, Philipp Rosenberger and Clemens Linnhoff will give a presentation about the performance and what the switch to flat buffers would mean for OSI and for the applications. So let's get started then. Into the introduction to ASAM and OpenX, I was asked to keep this quite short. If you have some further questions and maybe you're interested in joining the project or ASAM in general, feel free to get in contact with me. My contact is on the last slide. ASAM is a non-profit standardization organization within the automotive industry, and we focus on implementation level standards with this, which is a difference to the approach of ISO or SAE, for example, which focus more on the process levels. The ASAM standards are more recommendations. They are not the basis for lawmaking. And we do have a non-competitive open standard development approach, and where all the companies can come together and just work on the standards. And last of all, we are membership driven in all of our standardization projects. On the next slide, there is an overview of the current members. Take note, this slide is a bit outdated, but it still can give you a general gist. We do have around 350 member organizations all around the automotive industry and even beyond. And basically all of the big players are members. We have standards in 7 domains: so simulation, the data management and analysis, test automation, measurement, calibration, diagnostics, ECU networks, and software development. ASAM OSI is one standard within the simulation domain, and this is also the domain I'm going to talk about a bit further, because there are quite close relationships between all the simulation standards. And here you see an overview over the other ASAM OpenX standards. We do have OpenDrive, which is a standard that allows the description of static road networks. We do have OpenCRG, which is an add-on to OpenDrive and allows this very detailed description of road surfaces. We do have OpenScenario, which is the second part of this trio, basically, and allows the description of the dynamic parts of the scenario. We do have ASAM OpenODD, which just finished the concept phase, and we are about to start the standardization process, and it allows the definition of operational design domains. We do have OpenLabel, which recently had its 1.0 release, and it allows the standardized labeling for objects and scenarios. We do have ASAM OSI, which you know, of course, and we do have an OpenX ontology, which is about to have its pre-release. And tying all together, we have a study project about test specifications that just finished. The white paper will also be released in the next weeks. So that's it from my side. I hope I could give you an overview over the standardizations that ASAM is driving in the area of automated and autonomous driving. And I'll hand over to Kmeid.
Okay, hello everyone. Thank you for this introduction. You can hear me, right? And you can probably see my screen right now.
Yes, we can.
Hey, perfect. So let me go ahead. So my name is Kmeid Saad. I'm from ANSYS, project lead for the OSI extension. Throughout this year, so to say, heading towards 3.5 currently, but as previously Stefan have presented, the focus is here on Flatbuffers and performances to give a first, let's say, feel and first introduction of what's going to happen and whether it would make sense in the long term or not. But before we get into that, the welcome and introduction have already been done by Stefan, so I will just give you a short development update on OSI 3.5 or in general on OSI, and then some aspects or some working ideas or topics that we are working on for OSI 4.0. These are splitted a little bit. Pierre will take over when it comes to the performance, Flatbuffers, and some more update on the road model. And finally, Philipp and Clemens will tell you more about Flatbuffers, the technology, the performance, the more or less the need for it, and probably as well the plan toward doing this investigation. I'm not sure how many of you are already available with the working model on in OSI. I'm sure in general within ASAM it's a little bit different for other projects. However, for OSI, everything is actually visible on GitHub. So you have ASAM OSI on GitHub where you can see the developments, the pull requests, the comments, the merge requests, whatever. Everything is over there, the issues, feature requests. So it's open to anybody in the world, so to say, and as well as, of course, for ASAM members. And both of them can always give feedback or ask questions or raise issues or debug something or whatnot. The advantage or the point or where it differs from people that are not members of ASAM and the people that are members of ASAM is that basically all of these features are then in general analyzed and post-processed, let's say, by ASAM members. So these are freewheeling people that love to work on this and have the same drive toward the further development of OSI. Currently, we started with 4 main working groups. That's the sensor modeling working group, that's the traffic participant working group, harmonization with OpenX working group, and performance and packaging working group. So current ASAM members for OSI are diverse or are distributed over these 4 working groups. And most recently, there is also the Roadmodel working group, which was a result of the tendency or the desire for the harmonization with OpenX, where this group is now working toward, let's say, the restructuring probably and the investigation of the current road model in OSI and how to better match it with other OpenX standards like OpenDrive, for example, as the main focus, but others as well. So basically, these ASAM members actually take these pull requests or analyze these issues and features or even create them as well. And then when they are at a specific level of maturity, they are sent for a CCB, so control board, let's say, control board group, which is it's a number of representatives of these sensor modeling groups or subject matter experts, let's say, that take another look onto these pull requests from a different set of eyes, and if you want to say that, and they give feedback to GitHub directly to the actual pull request, saying, okay, everything is satisfied, documentation is set, the style is correct, the dot proto files are meeting the desired specification, and there are no strange behaviors or unexpected features or something that's actually disagreeing with what's the general intent over here. When that is done, the pull request is actually merged, and this pull request or this feature becomes a part of the standard. And this iteration goes basically forever. As long as the project is going, as long as there are ASAM members and groups and OSI and working on this, this continues and continues till there's nothing else available. You can access the standard directly from the ASAM website, where you will be prompted with the possibility of like downloading the release presentations, the user guides, the documentation, and the standard itself. Of course, you also have a direct access over here to the GitHub page that I was talking about, where you will have access to different repositories. These are for the packaging repository, where you can see how sample codes are generated and available for creating functional mockup units within OSI or putting OSI inside functional mockup units, the standard itself, and yeah, some other repositories that are still under construction or still under further development, so to say. Links are here, but again, a simple Google search, OSI, GitHub, or OSI, ASAM OSI, you will directly be prompted with these links as well. And Last year, okay, this is 2021. Sorry for this typo, but we had 3.4 released, and currently we are through the development phase of 3.5, which had a milestone set for now 2022. And after version 3.5 will be released, there will be a new project proposal provided for version 4.0. In general, version 3.5, I just placed here a little bit of some pull requests that are already available and that are active, let's say, up to a certain level. It's very important to note that these pull requests for 3.5 or to make it to 3.5, they need to be backward compatible. So non-backward compatible pull requests that have major changes need to be in only major releases can be released or integrated or actually merged. Aside from that, currently there's work ongoing for ground truths and feature configuration messages, timestamps to better address them for each moving object, so it will have another property or attribute to it. Other stuff related to mesh approaches, pedestrian classification. This is quite a new topic for pedestrian classification to be added in the sensor data as well. And yeah, so here we have longitudinal rotation of lane boundaries. This is a pull request over here right now, but again, as I previously said, there are work on the road model, so this is under investigation, so to say, to see in which actual version or actual release plan this will be then merged or diverged to. And as if part of the work that is actually being done right now for version 3.5, the group also committed to proposing and sending recommendations for version 4.0. It's a very important step to ensure continuity and to ensure that topics or efforts that have been done throughout this development period till 3.5 is not lost, and that newcomers, let's say, have a good solid foundation to start from if that's actually desired and needed. For version 4.4, as I said, it will be a new project proposal, and it will be focusing on non-backward compatible features and the harmonization, or the if I don't want to say the harmonization, the alignment with ISO 2315, which have already been released. So that being said, toward ASAM OSI version 4.0, there are already some current identified topics. Roadmodel working group, Pierre will go a little bit more in detail into that, so I will skip this for now. But then there is an important topics on the environmental model that also includes harmonization with OpenX. And here on the environmental model, I'm referring to the weather conditions in general, to the way we say, to the way we express, let's say, how rain is falling. Till now, it's in an ENOM stage, so heavy, light, or whatnot. For example, just for precipitation, there is also a strong request regarding extending this to include some float values or some double values for that. So again, all of these changes will directly affect the current state. So these are non-backward compatible changes. The traffic agent updates, I have a separate slide on this. I will go into that in a moment. And then there is also a alignment that's ongoing with the output or the efforts that have been done in the set level project to better define and to better align the definition messages of the sensor view for LiDAR and radar. Camera is usually in OSI the most mature till now. You will see probably in the Flatbuffer story how would that also make sense for example, LiDAR data, if you want to send it as a raw data, more or less. And the sensor view configuration process or sensor view configuration message is also a part of this. The main difference between them is basically sensor view configuration tells the LiDAR or the radar, let's say, its field of view or its firing sequence, number of antennas, position, wavelengths, stuff like that. So it configures the actual LiDAR, or it tells the simulation environment how to configure, how it would like the sensor model to be configured, so to say. I wanted just to point out this this traffic participant model that was part or a major outcome of the traffic participant working group. Basically, not to go into more depth or detail on the traffic participant model itself, but just to point out this traffic update message, which is the first in OSI throughout runtime. Let's say you will have a feedback control going back to the environment simulation. The reason I'm pointing this out, like everything else more or less stays the same, in addition to some additional message for the traffic participant model. I'm showing that just because we are currently discussing in the sensor modeling group similar approaches for a feedback control. That's again just a draft. This is just the output of the last meeting we were having in the sensor modeling group on, like, we know there's a necessity of getting that as well from a sensor model or even from an environmental effect model back to the environment simulation. For example, asking for exposure time adaptation or maybe ROI adaptation or whatnot. So these discussions are currently ongoing. Probably, maybe someone over here is also interested in something like this. Please feel free to contact us on this topic as well. If you have some strong beliefs on why something should be in one way or another, or if you just want to give your opinion on that. Specifically, tier one suppliers, this would be a very important feedback to get from you guys on these aspects. And basically, that was it from my side on the what's going on right now and what have been done and what's going to be done in the near future. I give it to Pierre if there are no questions. Okay, then Pierre, please go ahead. I'll stop sharing.
Yep, I'll jump in. Just a second. Should now start to see my slides, hopefully. So also welcome from my side. So many of you already know me and us from the OSI development right now for the current OSI projects, among other things. I'm the nominal lead for performance and packaging, and I'm involved also in many of the other work packages. So this is a short update on some of the other things that have been happening or are happening towards OSI 4.0. And just as a reminder, OSI 4.0 is the first major release since OSI 3 was released a couple of years ago. So this will be the first version or the sole version for some time to come, where we actually have the ability to break backward compatibility because it's a major release. So for that reason, we have been gearing up to trying to find out what actually needs backward incompatible changes, what would make sense for OSI 4.0, because for the most part we have of course striven to make most of the improvements to OSI happen in minor releases, since it's always nice to stay backward compatible and just incrementally improve stuff. But there are certain points where that's no longer the best way forward, and so to that intent we focused on a number of areas for preparing an OSI 4.0 development project. And one of the two has been the road model, because OSI itself, unsurprisingly, did have a very large focus on the sensor modeling point of view, which was one of the first reasons why OSI was widely adopted, because that is an interface that is needed in order to, for example, incorporate tier one sensor models into OEM simulations or similar kinds of setups. And the OSI 3.0 road model is very well suited for the sensor models that were in mind when it was developed. And it has worked there fairly well, and it also kind of matches what, on the other hand, sensor models have as the output interfaces. If you look at the ISO standard 23150 for the output side of sensors, there is a certain correspondence to what we have on the ground truth side of things in the OSI road model. However, what that also entails is that there are certain missing details. For example, the current OSI road model doesn't give you much idea of the road surface in the sense of how is the road surface shaped, curved, or whatever in between lane boundaries, because we don't have that information for the most part. We also have other missing details that have come up that would be good to add for certain use cases. It is not a very good match for the traffic participant models that we introduced in OSI 3.4 and during the development of those versions, in the sense that it is missing certain information that traffic participant models would want to have. It's also presenting information in ways that are very well suited to sensor models, but not that well suited to traffic participant models in a certain sense. So they will have to do more work to find out where they're located or how the actual lane layout is and so on. That's not really necessary for the most part. And we also have some alignment issues with OpenDrive. There are reasons why OpenDrive and OSI are not the same in terms of the road model, not the least of which is that OSI, of course, should be usable with measured data and other data sources that are not OpenDrive. But still, we want to strive to support OpenDrive as best as we can, in the sense of if you use two ASAM standards like OpenDrive and OSI together, you should have a fairly frictionless way of using that. So with those problems in mind, we set out to better support traffic participants, especially with logical information. So, for example, possible paths across intersections, which is not the same as lanes per se, because you might have an intersection where they don't have any lines on them. Still, you can say what are possible paths. Multiple logical lanes on a single physical road or lane, for example. So if you have a country road that doesn't even have any markings, you still are going to assume that there are two lanes going in opposite directions, which again is not something that we would be showing in the ground truth data right now. Traffic rule information and other stuff. I mean, this is not a complete enumeration of everything. We want to have at least some approximate road surface shape information so that, for example, traffic participant models can be positioned so that their wheels actually touch the road's surface and are not at odds with it. So that's stuff that needs doing. We want to have better alignment with OpenDrive, and we want to fix some of the currently underdefined parts. So, for example, we have issues in how lane boundary height and width orientation is supposed to be interpreted. And that's also something that we want to fix going forward to have a more portable approach to that. As part of this, road network modeling kind of subgroup was established and has met now for numerous times in order to explore those issues, and especially to come up with a position of how much of this can be done in OSI 3.x and what would be needed for OSI 4.0 kind of release. So do we need something incompatible there or not? As part of this group, quite a number of approaches have been examined and have been discussed. So we played around quite a bit with stuff. And we currently are getting a set of proposals that seems to be coming together. All of this is tentative, so the work group hasn't finished its work, but at the current point in time, it seems like we are converging upon a set of proposals that would make sense for everyone. And this points to additional layers of information to be added, so that we have the logical kind of information on top of the more physically oriented information that we have for the sensor models, and to unify them where that makes sense, but to keep it separate where it doesn't make sense to merge all of this into one set of information. We have a surface lines proposal and some other proposals of how to approximate the road surface description to a certain degree. We have some clarifications of how OpenDrive to OSI mapping would be happening in that sense. So this is moving forward at a nice pace, I would say. The good message out of that is that potentially many of those proposals can actually be added as minor or incremental changes. So our first assumption that we need to completely redo the road model itself is kind of moving more to the wayside. It seems that we can keep quite a bit of what we currently have and just incrementally enhance and change it to a certain point. However, it still might be the case that we want to or need incompatible changes in the OSI 4.0 timeframe. So, for example, we can take this opportunity to at least do certain cleanups that otherwise would be not possible to do in a minor release. So in that sense, it is still a good fit towards OSI 4.0. We can take advantage of this, but currently it points more towards it being evolutionary in a certain sense rather than revolutionary at that point. So it currently doesn't look like the OSI 4.0 road model will be completely different in a certain sense than the OSI 3.0 road model, at least for the current users. I mean, there's going to be much more information, and for traffic participant models, you really would want to take advantage of that, and for other models maybe as well. But it's not going to be completely dissimilar to the OSI 3 road model in the sense that you wouldn't recognize it if you looked at it. That being said, for OSI 4.0, probably there is going to be some changes that where we take advantage of the ability to do some incompatible changes for stuff, for example, that's completely underdefined right now, hence fixing it seems like a good idea. So that was the road model side of things, and now we come towards the topic that also gave this workshop its title, and you will hear much more about this in the presentation that comes after me from Philipp and Clemens. But I just want to set the stage for why we are even discussing this, or why we have been discussing this actually for quite a long time. So currently OSI uses more or less for historical reasons, Google proto-buffers, both for the IDL, so for the definition language, but also for the encoding layer itself. So the on-the-wire encoding for OSI, unless you do something special, is and has always been Google proto-buffers. And that has been a historical choice that already didn't quite completely match the way that OSI is being used in practice very well in certain areas, but it could be made to work, and I mean it's working right now. That's the way you're using OSI for all likelihood, and it seems to be working for many users. The problem is, of course, that now that the amount of transmitted data is really increasing, so we are adding more stuff to OSI in terms of increased level of detail, additional information, and as you see, we'll be adding quite a lot more going forward for OSI 4.0, for traffic participant models, for other kinds of models, for physical or reflection-based sensor models, which are not object list-based per se, but rather are working on detections or reflections or ray tracing information and so on. The amount of data that's being transmitted and the kind of data that's being transmitted is increasing and is getting more complex in terms of how it maps to Google protocol buffers. And we're also seeing larger use cases. So for example, we are seeing full-blown use cases nowadays where you have lots of sensors being involved, where you have lots of traffic participants and so on. So again, this is heightening the need to actually do something about performance. And that's where we come to the problem of Google protocol buffers. More or less, Google protocol buffers was designed for a very specific use case in mind, and that use case at Google was actually to transmit data between data centers for logging purposes, for other purposes. And the one thing that's true for Google in that setting is that computational resources are cheap for free for Google for the most part. Wasting a couple of CPU cycles is not something that Google frets about. However, even for Google, interdata center communication is really bandwidth and latency limited, and especially bandwidth limited. You are paying for bandwidth. So you want to minimize the amount of data that you're transmitting there. And for that reason, Google Protocol Buffers is geared towards trying to spend computation resources to minimize the data that needs exchanging. So it has special encodings for integers, for example, that try to use the least bytes to transmit small numbers, for example, stuff like that. The downside of that is, of course, that on current CPUs, this is really not a good idea in terms of CPU performance. Again, something that Google didn't very much care about because they were not CPU limited. And it also leads to characteristics that if you, for example, just change one number in an OSI message, and you re-encode it, you actually are going to get a different message completely potentially, even in terms of layout, because the field sizes will change in size just based on the data that's contained in them, even for numbers, for example. So really, you can't do in-place access, you can't do in-place modification, and so on. And if we look at OSI, on the other hand, that's really not a good match to OSI at all. Because really, for the most part, the way that OSI is being used, you try to stay on a single system image. You are not trying to do simulations based on OSI where one part of your simulation is running in one data center and the other is running in a data center on another continent. Because if you're trying to do that, you are already being killed by latency in terms of simulation performance. So really, you are going to try to stay on a single system image in that sense. So most of the OSI data is actually shuffled around in main memory or other high bandwidth attached memory. But spending lots of time encoding and decoding data in a very high cycle rate kind of environment like sensor models, for example, is something you really want to avoid. Also, for example, for sensor data, what usually happens is that the amount of data more or less stays the same between frames, but the detail might change and so on. So incremental updates might be something that's nice to do, not completely re-encoding everything just because you're changing a couple of bits and so on. Might be options that you would want to explore, which again, using Google protocol buffers is not really something that you can do. So already more or less right from the start, right from when OSI 3 actually saw the light of day, the thought has been that Google protocol buffers is nice and good to get started, but really looking forward, we probably, in order to grow, we need to look at alternatives to see how we can improve performance and actually match better the way that OSI is being used to the encoding scheme. So with that in mind, in the current development timeframe, we have the performance and packaging group that had the goal of looking at this and that set about trying to find alternatives and also from Google, but a different part of Google, Flatbuffers is an alternative that comes to mind, not the least of which because A, it's more geared to what we actually kind of need in terms of encoding, but B, because it can be made to work directly out of Google protocol buffer IDL descriptions. So it is compatible on the front end side of things if you are careful of what you use in terms of feature sets, and we were always careful there. So it is something that we can more or less do as a drop-in replacement in terms of taking our definitions and using them with flat buffers, which is something that's nice, but gives us a completely different encoding and completely different performance profile. And so the goals were to enable the use of the OSI data definitions with flat buffers to determine whether the actual performance benefits match what we anticipate and actually match what we need, to determine the effort to port models and implementations over, because while we can do a drop-in replacement on the definitions, it's really the API to encode your stuff in flat buffers or to decode stuff from flat buffers is different and by necessity has to be different than the protobuf API. So there's going to be effort importing stuff over, and we want to get a handle on that. And then we will have, at some point in time, we will have to have a decision on what the main encoding for OSI is going to be, because really supporting multiple encodings, while theoretically possible, really doesn't help in terms of compatibility, because on the wire, the encodings are not going to be compatible. So if you then get 5 models all using OSI, but all using different encodings, yeah, you don't have a working system, so it doesn't really help you very much. And so for that reason, we need a decision of how to go forward, and the work going on should be there to support that. And on the current status of things, so the initial port of OSI to flat buffers was done and is part of the OSI 3.4.0 release. So if you switch it on as an experimental features, you can get already in OSI 3.4.0, you can get the flat buffer version of OSI. You can use it as is, but what's not done there is example code, documentation, and so on hasn't been updated in the sense that flat buffers is now the encoding, because it's just an option that you can try out in OSI 3.4. We are also in various projects, like publicly funded research projects. We are seeing that we are running into performance limitations using the protobuf stuff in actual usage. So we have increasing experience with, for example, using reflection-based sensor models with the protobuf encoding and what that entails and what the overhead is there, and also getting more measurement data there. So that has been encouraging us to move forward. And we have now defined a work package for a service provider to port some of the models over to the Flatbuffer version of OSI and to benchmark those in a more rigorous fashion so that we can actually get to a decision point where we can say, okay, we now know what the effort is going to be to port stuff over. We know what the benchmark improvements are going to be, what the performance profile is going to be. We have all of the data to make a decision in the OSI 4.0 development project to say, do we switch or do we stay? And the good part is the service provider has also been selected on that, and we're happy to kick off that work package and the community discussion on all of this today. I mean, that's why we have this workshop as well, to get everyone involved in the discussion, because this will have a large impact, but it is also crucial in the sense that it should make OSI ready for the next couple of years. Because something to keep in mind is that we rarely do, and for good reason, we rarely do major releases of OSI because of the backward compatibility breaking stuff. And so OSI 4.0 will probably be the version of OSI for the next couple of years. We are hoping not to have to do an OSI 5.0 anytime soon. So really, these kinds of decisions have to be well understood and have to be well documented and agreed upon, because this is one of the core issues for OSI, is to keep the community together. And the last thing we want to have is we want to have fragmentation on OSI. So that's why we think this is a crucial decision to discuss and to be transparent about what it means, why we're doing it, and where we're going. And to not keep you that much further, because you will get more information from Clemens and Philipp on all of this. Again, just a recap, the reason why we're discussing all of this is that really Google protocol buffers are really not a very good match for the kind of encoding that we need for OSI even today. But we are increasingly running into these issues, and we are seeing that there are quite a number of benefits to switching to something that's much better suited. Because, for example, then you can do stuff like in-place data access, so you can access the data without having a separate decoding step. You can pick out which data to decode, more or less, to only be the data that you actually need, rather than the Google protocol buffer way, which completely decodes the message and then you pick the data that you're using. You can do in-place data mutation, which is interesting for example, sensor models that are outputting something where you say, hey, not much has changed between cycles, so we just mutate the stuff that has changed and then send it out very quickly, and so on. So those will be the major reasons why we're discussing this and why we're thinking about this. And just to put a very abstract handle on the performance differences we're talking about. So this is old benchmarking data, but it still holds true more or less. That just shows the orders of magnitude difference in encoding overheads that you see between Google protocol buffers and Flatbuffers, for example, or other more optimized ways of transmitting data. And that's really stuff like that, where you see that for 1 million times decode effort or encode effort, you are seeing 2 orders of magnitude at the least, potentially 3 or 4 orders of magnitude difference in the amount of CPU time that's needed. And again, this is getting increasingly worse on modern CPUs because, for example, all of the characteristics of the Google protocol buffer encoding really play against what current CPUs and future CPUs are good at. So it trashes branch prediction and so on, because all of that is data dependent branches and so on. So again, this is not something that's going to be become much better going forward, but it's actually going to become worse for all likelihood. And that's the major reason why we're looking at this. So that's been my update of the things. And with this, I would also be open to questions, and otherwise we can move on in the agenda.
Thank you very much. Are there any questions at this point? Doesn't sound like it. Okay, then I'll hand over to Philipp.
So I hope you can hear me and can see PowerPoint.
All great, yes.
Perfect. Good. So at first, before we start with the more technical stuff, I'd like to introduce myself. So my name is Philipp Rosenberger, and together with my colleague Clemens Linnhoff, I've recently, actually, end of last year, started a spin-off from Technical University Darmstadt. It is more or less based on our research and our experience we've collected there, and will be very much connected to the facilities at the Institute of Automotive Engineering there. So probably some of you know us from different research projects we have been participating, and now we have started our spin-off. And we are very happy, actually, that our offer to be service provider for the ASAM for this interesting project, transferring OSI to Flatbuffers, has been accepted. Before I start, short introduction of our spin-off of our company. So basically, we concentrate on 4 blocks. Of course, we have a lot of experience with sensor modeling, not only object-based but also reflection-based models. For example, if you have a look at the models we've been putting open source out of the university, and we offer services in sensor model customization to really specific sensors, so sensor systems. This is one block. The other is, and I see a lot of potential over there, is sensor model validation, to use test tracks, to use, but also smaller experiments for sensor model validation. We put a lot of effort into methods for requirement analysis. So, for example, the combination of the Percolect and Zebra methods we have been publishing. And the last block is of course perception algorithms, but simulation-based development, and using simulation to generate more data, or to generate the right data, as to say. And one block that's a bit in gray scale here is the standardization of interfaces. So we will be involved, and we will push forward OSI as much as we can, because we see it's one of the major basic requirements to do all that stuff. And yes, to kind of give them impression why we went to the decision, or got the expression actually, that we need some improvement on the performance, is here a result from the set level project. From the midterm event, there's been a lot of investigations on the performance of the different sensor models that have been developed over there during the project time. So there are videos available on YouTube, for example, explaining the model, the framework, and so on. And you see that for reflection-based models, there are a lot of reflections actually computed in simulation tools. In this case, it's CarMaker. but all tools that can support reflection-based models via OSI could be plugged in here. And then the right side is the actual reflection-based model that computes out of the reflections the actual LiDAR detections, the actual point cloud, and then can also, for example, plug in object detection, object tracking, object classification algorithms that have to compute the bounding boxes that you see there as well. Just to give you an impression. And of course, you could always think about performance of the actual model part, but we do not concentrate on this today. There's also a lot of potential in the actual interface, in the packaging, and so on. And short look onto the interfaces. So in this case, for this specific example, I've shown the video. It's a LiDAR, reflection-based LiDAR object model. Actually, here's the framework where it is built in. So you get in on the left side, you get in sensor view data. So it's not only the ground truth moving objects and stationary objects. In this case, for the reflection-based model, it's also the LiDAR sensor view. And there are a lot of reflections actually to compute. I will go on to this next slide. But you see all the processing that happens in between the model. So of course, this takes some time. Of course, you can visualize it as you've seen in the video to ROS, to other formats, to output formats. And then at the end of the model, you have sensor data, so detected moving objects, and so on. And if you have a look on how it is done right now, so the sensor view and the sensor view configuration, and this is work currently ongoing in the set level project, is that there is not a completely covered field of view, but you have specific areas where you have LiDAR beams hitting objects, and you have most of the field of view which is free of any light. And currently, how it is done in the current OSI version is that you have the schema, you have a very regular schema for sending out rays into the scene. And so this was the first item we concentrated on, or has been concentrated on in the project. If you see a photograph of this to get an impression from a master's thesis, so there, as I said, a lot of the field of view actually is not covered. And we in the project, we are changing the LiDAR sensor view configuration that is telling the environment simulation tool and the rendering and ray tracing tool where to send the rays in a more flexible way, in a totally flexible way, actually. So we can cancel a lot of rays to send to the model, and this helps a lot with performance, of course. So this is one point. The next is, okay, if you have the rays sent to the scene right now, because we have this regular schematic for the rays and for the reflection results, you have to send every result, even if it is not actually a hit point. So it's just limited by the range limit for rays, and then it's just computing nothing actually. But you have to keep the schema. And the next step, of course, is then to have for the input of the sensor model, for the actual sensor view, you have to send less rays than afterwards. So this is also one point that is addressed. Of course, you could think about sending less rays and do more efficient modeling. So just to go one slide back, sorry. If you compute the reflections, we do it, or it is often done with oversampling of the beams. So to play this video again, if you send out a beam and you would like to do this with ray tracing, you actually have to kind of oversample one beam and the beam divergence with multiple rays. So you have to decide how many rays you actually send for a beam. So yeah, the granularity and also the order, the scheme for one beam. Yeah, you have to think about this. So to go yeah, back to the slide. This could be done with less rays or with different yeah, ordering of the rays. Okay, so this is all ongoing in the set level project, and so it is not part of this kickoff meeting. Just to give you an impression, so it's not the only solution or the only thing to follow on to change from Protobuf to Flatbuff. And now for this, I hand over to Clemens to talk about the change.
Yeah, thank you, Philipp. I'll just quickly share my screen. I should be able to see the PowerPoint right now. So before we go into the Flatbuffers implementation, what Flatbuffers actually is, let's just crunch a bunch of numbers to see what the set level improvements would bring, just in theory, because maybe that's enough. Maybe we don't need to change to Flatbuffers because maybe the performance will be enough with the changes done in set level. So we just take a simple example. We take a widely used Velodyne 32-layer LiDAR. It's 360 degrees spinning in azimuth. Has elevation angles from -25 degrees up to 15 degrees. So 40 degrees elevation in total. We have certain beam width and beam heights, and then we set a discretization because of the super sampling we are doing in a ray tracing engine, and we just a little bit randomly pick 3 rays per height. Comes down to 0.03 degrees discretization for the rays. And then there's another thing with the current implementation of the LiDAR sensor view configuration in OSI, and that's set on a symmetrical field of view. As I said, the elevation is from -25 to +15 degrees, so it's asymmetrical. That means we need to put rays out also above 15 degrees to +25 degrees, making this, instead of 40 degrees, 50 degrees elevation. And all of this computes to a whopping 20 million rays we need to shoot out. First of all, I don't think any ray tracer can handle this in any timely fashion on a desktop hardware. And then again, keep in mind, nevertheless, if these 20 million rays hit anything in the scene, they need to be transferred from the ray tracer to the model. So not only would be the set level improvements an improvement, but they would make it possible to use it, for starters, for higher resolution and with a big field of view LiDARs. If we take the same numbers with the improved model, of course, we have the same boundaries here in terms of field of view, but now we take into account the actual beams. So we have 900 beams in azimuth direction, and we have 32 layers, as I said. Same divergence, same discretization, and then we just assume that only 80% of the rays hit anything in the scene, so generate a hit point, and then we get this 20 million rays down to 400,000. So a really dramatic improvement already here. So now the question is, these 400,000 rays and corresponding reflections, how much time does it take to transfer them from one FMU to the other? So from a tool, a ray tracer, to a model. And we just took a quick example. We just modified the OSMP source, like dummy source example that's in the OSMP repository, and just basically hacked in that it transfers also reflections. At the moment, it's only for object-based models, or it's an object-based source. So we hacked that in and just randomly transferred 400,000 reflections. It doesn't matter where they are, we just want to estimate how much time it takes. So we have a source serialization. We connected a kind of sensor FMU that just deserializes the data, puts in a bunch of detections, and serializes it again. So we have 3 steps of serialization and deserialization. And in sum, this takes to about 100 milliseconds. And if we look at the sensor, it runs typically at 10 hertz, so also 100 milliseconds. So if we want to get to somewhere real-time performance, we are wasting all the time we have just on serialization and deserialization. And especially the deserialization in the model takes up the most time. And yeah, there's the promise, or in theory, Flatbuffers should decrease, especially this time, by a lot. So it's still problematic runtime. And keep in mind, this is only one example. The more advanced, the more advancements there are in LiDAR technology. We have 64 layers LiDAR. We have 128 layer LiDARs. So this problem will only increase. So let's take a look at Flatbuffers. First, in theory. So this is just taken from the official documentation on Google. What does Flatbuffers promise in theory? And then after that, we will have a look at the actual application. So we'll keep the theory short and then look into how what does this mean for me as a sensor model developer to use Flatbuffers. So Flatbuffers is a cross-platform serialization library for a bunch of programming languages, 2 of which are C++ and Python. I think the mostly used with OSI, or the mostly supported in OSI. It's originally created by Google for game development and especially for performance-critical applications. And I think, as Pierre already said, it's all open source and available on GitHub. Some of this stuff Pierre already mentioned. So the promise is that we can access serialized data without the parsing. So the deserialization time would decrease or get close to nothing. Should be very memory efficient because we can directly access the data in the buffer with pointers, and we don't need to deserialize and store it in some other variable or class. It will be very flexible, so fields are optional, and for further minor releases, fields can be added, keeping backwards compatibility then to the 4.0 version, so the first Flatbuffers version, if this will be implemented. The footprint, so the headers themselves for the Flatbuffer are quite minimal, as minimum dependencies. So not a lot of overhead there. And one of the promises that most errors will happen at compile time, and we will not run into as many runtime errors, probably as we have with protobuf at the moment. So how does Flatbuffers work? The basic stuff is kind of similar to protobuf. We have a schema file that's similar to what we have in the proto files right now. Actually, they can be converted into one another. And we have a definition of the fields and on the whole hierarchical structure we have now. There's a Flatbuffer compiler that takes these schema files and automatically generates header files. So also similar to what we're used to with protobuf at the moment. And then there's a Flatbuffer builder function that helps us create the flat binary buffer out of our data and out of our variables we have. Of course, you can store the buffer and send it anywhere. So keep it on your system, send it over a network, whatever. And then reading the buffer is as simple as getting a pointer to the root object, and from there just going through the data structure we have. So the overall advantages should be there's no need of kind of unpacking objects. You can directly access them with the pointer, and also the code, the overhead in header files and so on should be less in Flatbuffers. So far for the theory. Let's now take a closer look into the application and what it actually means to use Flatbuffers. Keep in mind that we, as a service provider, just started now looking into Flatbuffers and OSMP and OSI. So this is kind of a first experience we gained, and we can discuss afterwards maybe what your experiences are if you also have experiences. So first of all, let's compare a proto file we're used to. This is just an example, an excerpt from the sensor view definition. So we have messages, sensor view, and then in there we have other messages underneath, and then we have kind of parallel, or not in parallel, but these messages down here are then in the proto file also defined underneath and so on. This is just an excerpt. And if you take the same excerpt for a Flatbuffers so-called FBS file, it's a little bit different language definition, so different, a little bit different in the syntax, but it's really similar. Instead of messages in Flatbuffers, we have tables, and we can also define like our own tables and nest them into one another. We also have what's here repeated fields. We have these vectors here, so that's all comparable. And these FBFS files, as they're shown here, are automatically generated from the FlatC compiler out of these proto files. There is a little bit of a difference, a little bit of a design choice, but I will get into that a little bit later. In one of the next slides. So this is kind of the definition of the buffer. And from this, with the compiler, with the Flatbuffer compiler, the header files will be generated. And these header files you can include in your models in your C++ code. Speaking of code, let's take a very small example, just generating a sensor view. So we generate in protobuf, we generate an OSI sensor view. We can add a sensor ID, for example. This is value 1 at the moment. And then we want to add one moving object to the global ground truth in the sensor view. So we generate a global ground truth in the sensor view. We get a pointer to that, and then we can add a moving object, set an ID, and set some coordinates, for example, here just X and Y to some random numbers. At the end, OSMP takes care of serialization. So we serialize it to a string, write it to a buffer, and we get the values we transfer over FMI to other FMUs, so base, high, low, and the size. And now let's look at what this looks like in Flatbuffers. Again, this is like first implementation. We're only just gathering experience. So this looks a lot more. But bear with me. We try to go through it, and I try to explain our understanding of how Flatbuffers work and how Flatbuffers with OSI would work. So first of all, for a buffer, you need a Flatbuffer builder. So that's the first thing you do. You initialize a builder with a initial size, but size will grow according to what you put in to the buffer. So that's just an initial version. The main difference, what we found, was that you cannot nest builders. So every table in Flatbuffers needs to be created with a builder. So every message, every sensor view, every global ground truth, every moving object is a message in protobuf and is a table in Flatbuffers. So we need to create them with a builder. And these builders, again, cannot be nested. So we cannot start with the sensor view, because we open up building a sensor view and then we would open up building an ID or a global ground truth. That doesn't work. So we need to start from the inside out. So we start with the position. And this create function is one function in the header file. That's essentially also a builder. It's just a convenient way to create this table, the vector 3D table, in one line. So we pass the builder we generated up here and pass X, Y, Z coordinates, same as here. Then we move further out to the base moving we generate here and create a builder. The difference between creating like this builder function instead of just using the create function is that here you need to define every single field with these more primitive fields. That works quite well, but with base moving, there's also a create base moving function, but then we would need to put in basically every value of the base moving field, which we don't have because we only have the position. So the version we're using here is creating this builder, adding the position we created up here to the builder, and then we finish the builder, and this is actually the serialization step. So so what protobuf does, it creates the whole data structure first, and at the end serializes the complete data structure. And Flatbuffers serializes individual parts, individual tables while they are created. So once we finish this, we just get an offset, and that's just the pointer offset from the root object to this in the buffer to this field here. And then we can continue. We can, in the same manner, create moving object. We add the base. Moving object is a repeated field, so we need to create a vector. Done that here, just a normal STD vector. We push it to the vector, and then there's a create vector field that can finish this and again creates the offset. Then we go on with the ground truth, adding moving object to the ground truth, and so on. The identifier, so we're kind of moving up here inwards to the overall root object with the sensor view, adding it to the sensor view. And we finish the sensor view, and then we finish the builder. And now we're done. We can, from this builder, we can get the buffer pointer. That's just the pointer to the root object. And we can directly get the base, high, low, and size from this. So kind of the serialization is done in between the code. Like while you're building up your data structure, it's directly serialized. Which yeah, at the moment, or from our first experience with it, looks like it's quite some more coding, but maybe you have other experience, and we can talk about this in a bit. So this was creation of Flatbuffers. Now let's talk about reading the Flatbuffers. So we're now on the sensor side. We want to get in the sensor view, and this is really simple. Or very similar to protobuf. I mean, here you have the deserialized object. After deserialization, you don't need to do this here. You can just directly, with pointers, go to whatever you need, for example, the moving object size here. In the protobuf version, we're used to functions like empty or these has functions. For example, if a moving object has a base, we don't have that in Flatbuffers, but we don't really need it because if an object here is empty or it doesn't exist, we just get a null pointer, and we can, which is by C++ compiler, can be converted into a Boolean. So it's kind of the same thing. And the last point, that's actually we're actually not that deep into this to make a final point here, but we're used from protobuf that we have mutable fields, at least in the deserialized object we have. We can change them. From what we understood at the moment, per default, the fields are constant, so cannot be mutated. But as Pierre already mentioned, there are mutable options. We found somewhere that it's not really recommended, but we will definitely keep a deeper look into mutating these fields. So this just as a first share of experience, what we've come up with in like the last couple of weeks, applying Flatbuffers to OSI and first trial versions, and there are some considerations. So as I said earlier, the messages in protobuf transfer to tables in Flatbuffers, and then every table is taken by a builder function to a separate part of the buffer. There's also a different version, and that's structs. So you can also put data fields into structs and not directly into tables. And from what we experienced, that makes sense for like lower level data fields like vector 3D, for example, or orientation 3D, fields that only rely on primitive data types, to put them into structs, because it just makes the handling of the code a little bit easier and might also bring runtime performance, but we're just starting to look into this. So yeah, we will work this out, give some examples, and then the community can make an informed decision on where we stand on that. Because the problem might be that then the proto files are not directly transferable to the FBS files, because the FBS files would be manually changed and in some form from tables to structs. But as I said, we will look deeper into this. So this will be a consideration to be done in the next couple of months while we're working on the first prototypes of Flatbuffers. So maybe before I go further with describing the in detail tasks we have as a service provider, maybe we can take a couple of minutes and share some experiences. Have any of you had any experience with Flatbuffers yet? Do they match what I presented?
Maybe one point, if you can go back to the slide where you compared the serialization code. Yeah, I think one problem on the right-hand side is that due to the lack of space on the slide, all of it is meshed together. If you group it a bit more, it looks less bad than it currently does.
You're right.
Would be one point from our experience working with it. And as you said, the one thing you have to wrap your head around in terms of Flatbuffer serialization is that it is not you build up a set of objects and then you serialize them, but rather you serialize in step. So the moment you create something, it is already being serialized. So you have to follow a certain order. There is some leeway, but other than that, you have to follow a certain order. And the other, so if you do that, I think it is definitely workable, and it will look more natural than what you are seeing here right now. The other thing to point out is there is an object-oriented API option as well. And that more closely matches the protobuf point of view. So you then create objects first and then do serialization, so that there is that option. That is, of course, less efficient then. So for very high efficiency cases, you probably don't want to use that. But for not so very high efficiency cases, it's still much more efficient than the protobuf stuff is. So that's also maybe something to look at. And then the code actually does look quite a lot closer to the left-hand side if you use that option.
Okay.
But so from our experience, it is definitely the case, and that's one of the reasons why we emphasize that people must get involved now. It is really different to work against protobuf versus Flatbuffers. So, and I think there also the important point to get across probably is with protobuf, there is the temptation to use the protobuf data structures as your internal data structures, because they support all of the nice stuff that you can do with it. They might still not be very well suited to your internal usage, which is why it is probably a bad idea to do it in the first place, but you can do it if you want to. The flat buffer side of things, if you want to be high efficiency, really points out that, hey, this is for external representation. If you want to work internally with the data, yeah, please use your own internal representation, which is matched to your algorithms. So that's the other distinction that you have to keep in mind, is that really Flatbuffers is about, I want to externalize something for someone else to use. It's not supposed to be the internal representation to work with the data. Whereas with protobuf, you can kind of pun on that and say, yeah, but I'm too lazy to come up with an internal representation, so I just use the protobuf objects. That's just the experience from our side.
Yeah, thank you, Pierre. I've taken some notes, and we will definitely look into the object-oriented API, and also distinguishing between internal and external data representation for the examples we will create. Anyone else with experience wants to share their view on Flatbuffers? Okay, then I will continue with
Yeah, sorry. So it's not really experience of using it, but it's deployment. I'd just say, like, internally within our data structures or within our communication messages and protocols for physics-based simulation, because you generally have a huge amount of data, whether you want to send raw data or whatnot, the Flatbuffers are usually the go-to protocol for us. Just talking from ANSYS point of view. Probably on object-based level, that's another story. But again, OSI is not like raw data is within the sensor view message as well, right? So it's just something good to see going forward, and yeah, I'm really hoping for the best to see how to work with this and to get it, you know, to get the final output, or to try and test it with a full, I don't know, 48 by 48 imaging radar, for example, like a 2K channel radar, for example, or something like that.
Yeah, thank you. We'll definitely test like high performance stuff on that and see where we can get with high resolution LiDARs.
Probably it's worth noting again that this is a investigation. So we are still, it's not that there has been a decision, Flatbuffer will be the solution. It's an investigation what we are doing here. And as we shared, it's not only an investigation on performance, it's also an implementation experience. Yeah, I mean, we are hoping for discussions with the whole ASAM or open simulation interface community. I think, Clemens, if you continue, and then we probably have some questions afterwards.
Yep. Actually, that brings me to the specific task, because that's kind of what we're here for as a service provider, to get some food into the discussion, to make some reference implementations, so everyone can try out OSI and Flatbuffers. So for starters, we will port the OSMP dummy source and dummy sensor implementation that's in the OSMP example folder on GitHub to Flatbuffers, so that it will work with the Flatbuffers implementation. We will present the results of this portation in the CCB meetings, and we will also make everything we do accessible as a pull request on GitHub as in the OSMP repository. And at the end, we will write a report about the implementation that again will be open access to the community. Then, like, this is a really minimal example just to see how it would work overall. And then we will take a more complex example, like our reflection-based LiDAR model that's open source. It's one has been developed in the Saad level project and is open source on GitLab. And we will port also this, gaining more experience and a more in-depth view what it takes to transform a bigger complex model to Flatbuffers. And then we will create a benchmark test suite for testing the protobuf implementation against the Flatbuffers implementation for the reflection-based model, but it will be universal, so also dummy source and dummy sensor can be tested with it. So we'll set up an open source co-simulation SSP-based system to test this, and for this platform, we will have like timing functions and an output of the timings in different FMUs in a JSON format. We will actually take a format defined also in the Saad level project, so it will be comparable to other results of that project. Just the evaluation scripts will be our own, so we will be writing Python scripts to evaluate the timing data, and yeah, we will also make this available. And also we will write not only a detailed implementation experience report, but also an evaluation report for the performance itself. So hard facts just on performance, where what's better between those two systems, also in different configurations. Our motto for this is open source through and through. So everything we do will be made publicly available, from the changes in the models and OSI we do to the code simulation. We will be using OpenMCX. It's an open source code simulation platform from the Eclipse Foundation, so that basically the whole process can be used by you from the code simulation to the models to the evaluation scripts. We will make public as Python scripts, and then in the end, all reports on performance and coding experience will also be available to the community. So because that's the idea, I think we've stressed this enough. This is not like an executive decision. This is a decision the whole community needs to take, because it affects everyone who will be designing sensor models, but also other models, traffic participants, and so on in the upcoming major release. As for the timeline, we will be porting the dummy source and dummy sensor models at first and in kind of a timely manner, so you can already have a look. We just for ourselves set a date at end of January, so end of this month we will make a first version of the ported dummy source and dummy sensor available as a branch on the OSMP GitHub. And then I have to jump a little bit down here because code simulation platform and also test evaluation can already be used for the dummies. Although, of course, the main interest will be the reflection-based, more complex model. But first version of the test evaluation will be made public in the mid of February. So you can already test that out. And then we will continue with the more complex models, and we'll make that public beginning of March. And then at the end of March, we'll have a final version also of the test evaluation. And also the whole project will be concluded. Like our project, our investigation into Flatbuffers will be concluded at the end of March with the final reports. Yeah, so far for the timeline and what our tasks are there any questions or maybe just interest? Some partners maybe say, okay, that's really interesting. I want to contribute. How can I help? Or you have just questions, feel free. Okay, I don't see any questions. Then thank you for your attention, and I will give it back to, I don't know, Stefan, Pierre.
All right, thank you very much. I'm a bit surprised that there aren't any questions or comments or anything, because maybe to clarify that again, this is a breaking chain. It will break your implementation when you update to OSI 4.0, and we really want to not make this switch light-hearted, and we really depend on input from the community if that's a good change we make. There is some upside, like the colleagues presented, but there is also the downside that the porting from 3.5 to 4.0 will be some major rework. So maybe I'm gonna try again. Is there some comment about the performance of OSI? Is performance an interesting topic to you? What do you think about the proposal to switch to Flatbuffers for 4.0?
Stefan, if I might just add to this, like, even if there are no questions right now or direct points or direct whatever, the important thing is to take out from this is, if we decide to move to OSI 4.0, it will be based on the performance tests that these guys will be doing, and in addition to that, based on the feedback that we get from OSI users. So if OSI users don't say no or don't say yes, and our analysis of the performance feedback from the service providers and from the current ASAM members is actually a positive one, then we will most probably be moving toward Flatbuffers, or not moving toward Flatbuffers, depending on whatever the outcome is. So as users, and now this meeting is not restricted to ASAM users, right, Stefan? ASAM members, sorry.
Yes, correct.
So as users, then it's really your chance right now and in the coming, let's say, 2, 3, 4 months, so to say, to just give feedback, raise your concerns, or whatever, whether that's from a software provider, whether that's from a tier one, or whether that's from an OEM perspective, or just maybe university or in academia as well. Any OSI user, really, you have the chance to do that right now. And I can't stress on this. Right? So this is really very important. You can come also with requirements. You can also come with requests for demos, requests for whatever, but it's based on your feedback. That's it.
Okay,
Philipp,
microphone.
it sounds like noise from your side only. You're moving your lips, but you're speaking a language we are not able to hear. It's partially supersonic or something. Still the same problem. I think you
really
need a new
noisy,
microphone or new connection.
Maybe just a few words from the OEM side, from BMW. In preparation to that meeting, we already had a discussion with colleagues from the sensor side part of BMW. And we are really interested in this topic. Of course, because of the performance optimizations we would like to gain by that. And also really open to Flatbuffers. And because the question was from your side, Kmeid, if you don't say yes or no, we're following up the topic, and we have our rounds where we discuss then what we experience in this project. So the interest is total, just that it doesn't look like no one is speaking here. We are really following the topic, and as you can see in the member list, I think around 5 or 6 colleagues are participating here. So that is just from the BMW side.
Yeah, sure. I'm just like that. Like nobody needs to say anything right now, right? So there is just putting it out there. I'm sure we will have reports to show as well, and to present and to publish. I'm not sure how the process of publishing all of this will take place, but I'm sure Stefan from ASAM will directly find a good way to make this public information for everyone. So just keep an eye on this, follow up closely on this, and feel free to contact us at any time, whether directly through Stefan or directly on GitHub, however you like, expressing whatever you need and whatever, I don't know, comments or feedback that you already have, or maybe previous experience again, or maybe your colleagues know about something, for example, right? So
yes, that's actually. Sorry.
No, that's it.
That's actually also why we put the timeline the way we did. So we wanted to have a minimal example for the dummy source and dummy sensor online, and then we can also keep the discussion there on the branch and as GitHub tickets. We will be monitoring, of course, everything that goes on there, and then we will hopefully have a lively discussion once we have a minimal working example.
All right.
Right.
Then I'm gonna take over really quick again, or is there anybody else who has some comments and inputs?
Just one more question. Maybe I missed the point. The presentation you did, Clemens and Philipp, it will be uploaded to the ASAM page?
Yes. All of the presentations will be shared, of course.
Okay, great. Because already this was a super summary of how protobuf and flatbuffer have differences, and super cool. Thank you.
So just as a last words again, we do need your input to make an informed decision about the switch, and for that, performance experiences and tests from real applications of OSI will be invaluable. So please help us here. And there will be regular updates of the mailing list of the project, just get in contact with me for updates. And you can also join the project. This is the link to the GitHub. You'll find it in the slide as well. And if you have any other questions, also feel free to get in contact. All right.
And maybe just to enhance on that, so all kinds of feedback are interesting here, and I mean there are multiple dimensions into which the discussion is going. So, for example, besides the pure fact of switching to Flatbuffers versus protobuffer and what that entails, there's also the question of we can, of course, still provide a protobuf version of it, but the problem is if we support multiple versions of the encoding, we don't have on-the-wire compatibility. So this is what I alluded to beforehand, is that we could generate out of the same IDL description, we could generate both Flatbuffer and protobuffer definitions as we do now. The problem is if we let multiple encodings be established at the same time, we will have the problem that you will then have to check whether a model is supporting OSI Flatbuffer or OSI protobuffer before you can even use it, and there's no automatic translation between the two. So for that reason, we are probably, if we are going to make the switch, planning to make Flatbuffers the main or even the sole encoding for OSI 4.0. But again, you might have feelings about that as well, of saying, yeah, that's all nice and good, but we want to have migration time where we support both of the encodings, even though we know that this can lead to fragmentation, or we don't want to have that. Please don't do that, because we'd rather bite the bullet than have fragmentation. So again, this is the opportunity for the community to chime in and say, hey, this is the way I feel about it. This is the way I would like it to go. And that doesn't mean you have to have very distinct experience with Flatbuffers or very distinct problems at the technical level. It's also okay for you to chime in and say, hey, just from a user's perspective, we'd rather not have fragmentation, or we'd rather have a transition period, or we have this problem or that problem, or this feeling or that feeling about it. Because again, the whole point of OSI is it only works if it's a community, in the sense there's wide adoption of it. And we don't want to lose that. But on the other hand, we have to do certain technical transitions. And this is our way of trying to manage that. So again, please don't feel put off by any of the technical stuff and so on. If you have any feelings, any opinions, please do get in contact with Stefan or the project as a whole on GitHub or directly. We'd rather hear from you than not hear from you. Is probably the message I want to put across. Thank you.
All right. Thank you very much for the summary again. Okay, if there aren't any further comments, I'd like to thank you for your attention, and get excited about the results of the Flatbuffer evaluations. Thank you very much.
Thank you.
Thank you, Philipp, and we'll learn your new language as soon as we can.